Hi, again for the recording, I'm Chris. If you'd like to follow along, there's a link to the repo where all this code comes from. That might be a little easier than trying to follow along because the snippets, I had to chop them up a little bit to fit them on the slide, but if you want to see the entire library, it's there. It's a command line argument parsing library that uses C++17, CMake 3.22, works on all OSs. The library exists for the sake of me demonstrating stuff, trying things out, so it doesn't exist necessarily for users, and I don't think it has any, but by all means, use it if you would like. As you can see from this talk, it is very thoroughly engineered. So starting off with an easier thing is you might not know that the project call in CMake has a description and a homepage URL. Below is an example of where that description might come into use. Later I'm going to talk about Doxygen sites and how you might generate those. And Doxygen is automatically picking up on that description variable and using it to populate that on the website, which is nice. The homepage URL is not all that useful if you're just linking back to your repo on GitHub, but if you do have a website that is separate from where you're actually hosting the code, then that can be a very useful thing to help make sure people know where they can find that. I won't talk too much about compiler warnings because this is somewhat controversial, and I think I've tried every single option for applying compiler warnings, and I've settled on this. So I'll just kind of leave this here for the reader. If you don't like how I do it, please come to the Burns and we can talk about alternatives. But I think it's safe to say that you should be using warnings, and I think among all the options, putting them in your build scripts is the best place to put them because you need to have compiler-aware warnings. And the best place to detect the compiler is within your build script. Installation is a bit of a mess. It takes a lot of steps, so I understand this is a big block of code for the slide. But there's a few things that you ought to know about it. First of all, please do it. If you're going to be installing, in particular installing libraries, the assumption is that you'll be exporting your CMake targets. That's not strictly necessary, but it's a de facto standard that you should be following along. There's two include modules that come from CMake that you'll typically see. That's the CMake package config helpers and the GNU installers. And I'll show you where those get used in a second. Something you need to realize about installation is that when you're specifying your include directories, you need to tell CMake whether or not this includer applies to building your project or using it once it's installed. So this build interface generator expression on this line is telling CMake that this includer only applies when you're building the library. If you omit that and then you try to install the target, you will try to install a header and include directory that points to where you had the code checked out. So obviously that's not going to work if you install this and move it, or if you install your library and then delete the repo from which it came, which is a valid thing that you might do. CMake will warn you if you don't do this, but if you're curious why you see this $triangle bracket build interface thing, that's why it's there. So for the installation, there's a few major steps. The first one is that you need to specify what headers to install. So in this case, everything in the include directory in my repo is getting installed. So that's what this command is doing. The next command is where I think a lot of the installation work is happening. So this is doing a number of things. So first of all, that top line, that export argon targets, it's creating what's called an export set. So in CMake parlance, this is really just a collection of CMake targets that you're going to install. The assumption is that if you install a given target, you're also installing all of its dependencies. So if you have a more complicated library that has multiple targets in it, CMake might yell at you about not having all those targets in your export set. So you might have more than just a single target in there. The runtime, library, and archive destination, what that's doing is it's telling CMake where you want to install these things. So roughly speaking, runtime destination is going to be things like executables and dlls on Windows. Library is going to be your .a files. I think .sos go there. I forget exactly all the rules for where things go. But generally it follows this pattern where the runtime destination is going to go in this CMake install binder, and then library and archive go in the CMake install libdir. Those variables are coming from this package right here. So what's great about this, or this module right here rather, what's great about this is that if someone is packaging your library, they can change what those directories are. So please, if you're going to write a library, be friendly to package managers. Give them some way to specify where your various artifacts of your library are going to be installed. I also like to tack on this right here, /argon-project version. What this is saying is, for example, the headers are going to go to include/argon-0.12.0, which is the current version of the library. The reason I do that is it allows you to install multiple versions of the library simultaneously. You don't need to do this, but I think it's nice to have. It avoids having multiple installs stacked on top of each other, which can cause some issues and be a little unexpected. So I think that's a nice thing to include, so you can install multiple versions. The third step is installing the export set. What this is really doing is just like generating a file. It's going to be called argontargets.cmake, and I believe also argontargets - whatever your current config is. You can add a namespace to your target, which is very useful. This is another one of those aspects of modern CMake installation that you typically see. What this means is that your library targets, which in this case is called Argon, is going to have this extra namespace tacked onto it. So in the install interface, when you consume it, you'll be consuming a target called Argon : Argon. The convention here is that the namespace is usually identical to the package name or the project name. Not strictly required, but it's a nice convention to follow. Last, you have this write basic package version file. What this is doing is it's generating a file which tells you whether or not you can use a library when what you requested is not identical to it. So if you request something like Argon version 1.11, but you have 1.12 installed, that will be allowed because at the end of this line, you can see same major version. The compatibility policy for this library is that it's just conventional Simver, like you might expect. Anything within the same major version that is as new or newer than what's requested will be allowed. So that's luckily almost entirely automated away for us. And then lastly, you're just installing the config module that you generated and the corresponding config version module. I know this is a lot. It's best to probably read this in the context of the whole code base. But hopefully you got a better picture of the rough steps for doing all this. Okay, something a little easier. If you have a library, you probably have tests. You should have tests. It's a nice convenience to allow people to opt out of building your tests. If someone is packaging your library, they don't care about their tests. They don't want to build them. They don't want to bother with them. A nice convenience for that is there is another built-in module called CTest, and if you include that, it will generate a cache variable called build testing, which is like the canonical way of enabling or disabling your test. It defaults to on, so just add a simple conditional to only include your tests if you have that cache variable set to true. Yeah, it's a little unintuitive. You'll see if build testing, but you won't see like an option that declares it. It comes from the include module. I should also note that if you include CTest, it also calls enable testing, which is another thing that's required to actually make your tests be able to run. So include CTest, and a lot of other nice things happen automatically for you. Likewise, for examples or any other optional part of your build that is not strictly necessary to using it, please have an option to disable it. This library has examples. Your library might have additional tests. You might have benchmarks as a good example. Anything like that, please give an option to disable it so you're not forcing people to build things that are not strictly necessary if all they want is your core library. I'll note if you're building an application, if it's not a library, you don't really need to bother with this. Applications are not typically packaged. You're potentially the only user of it, so you can skip a lot of this stuff for applications, but if you are making a library, then certainly all of these things apply. So this is a fun thing regarding the actual tests that you write. Test frameworks like Catch2, DocTest, and GTest all have a function that has the same name called the name of the test framework, discover tests. So right here, you pass it the test executable target name, and what it does is it will go through every test case in your executable, and then it will extract all of those into separate different tests that get registered with CTest. So what's nice about this is that if, for example, this Argon basic option, that class, if a test related to that fails, you'll only see this go red. All the 7 other tests will stay green, so you can zero in very quickly on what actually failed. On the right is what you have if you don't use that. You can see it's just a monolithic test Argon executable. So if anything from the actual core library fails, you're just going to see a single test go red, and then it's up to you to go looking for it. Yes, Ben?
So I tried this recently, and everything you said is true. There's an unfortunate part here, which is that the discovery function don't know much about the suites.
The Catch Discover test and the G test or Google Discover test don't represent your test suites properly. So if you want to run your test and only run certain suites, it's annoying.
There's a CTest flag called -R that you can use to filter subsets of your tests. I'm not sure if that's what you mean, but if I only wanted to run, for example, like parsers, like the main class of this library, I could filter on just only running that.
Yeah, I tried this about a month ago. It was doing that. But like, there are different filtering mechanisms. All testing frameworks allow you to put tests in suites, right? But CTest, I don't think that information, like it would be hard to get information through, but it's just not done properly in the Disco system.
Oh, okay.
So you end up writing, yeah, if you want to do that stuff, you end up writing patterns in the test names as like prefixes rather than using the actual suites as they were intended.
Mm-hmm. These do make some assumptions about how you organize your tests. If you organize your test such that these work well, then great, it'll work. If you insist on a different organization that doesn't really work with how these functions expect them to be organized, then it might not be as valuable. But certainly, like if you're just starting out, I would recommend using these, although for sophisticated enough test suites, you might want something that's more specific, so that's to be expected. Okay, shared libraries. Who loves DLLs on Windows? Big fan. Loves supporting them. Yeah, we all do. You're going to learn how to support them. If you don't support DLLs, ignore this whole slide. Almost all of this complexity exists for the sake of supporting DLLs. So if you're not supporting Windows or not supporting DLLs on Windows, then congratulations, you have the luxury of skipping this. But if you do want to support DLLs, which I'd recommend you do, it's not too difficult, then you're signing yourself for this much complexity. All right, so I actually want to start here. So this generate export header is a function that comes from this generate export header include module that ships with CMake. What it does is it creates a header, and I probably should have included a snippet of it, but it's basically a ton of defines that expand into the compiler specific attributes that are required to export symbols out of shared libraries. It's a lot, that was a big sentence. The idea is that on Windows, DLLs by default have all of their symbols hidden. So if you build a DLL and you don't export any of those symbols, even though you link to the library, you can't use any of them. So there's this kind of opt-in nature to DLLs, where you need to annotate every single symbol that you want users to use. So the good thing about this is that by default, everything is hidden. So if you don't want something to be used, you can simply not export it. So if you're thinking about Hiram's law, if you don't want people to depend on parts of your interface that they shouldn't be depending on, then that's a good thing for you. If you come from the Linux, macOS world where everything is public by default and thus kind of easier to use by default, then it can be annoying, but I think there's something to be said for hiding all symbols by default. So because in the Unix world, everything is exported by default, in the Windows world, everything is hidden by default, you have this line right here, which is telling CMake to hide all the symbols in your shared library. So there's two different properties. There's the CXX visibility preset, and there's visibility inlines hidden. So you opt into both of those, you hide all of them. So that what that means is that when you're building on Unix systems or really anything besides Windows, or if you're building on Windows, you get the same behavior where everything in your shared library is hidden by default, as opposed to the kind of awkward state where everything is hidden by default on Windows, but visible by default on other platforms. We want that to be consistent. So that target property gives you that.
I had someone recently tell me that they did this. Yeah, sure, I'll take the mic. I had someone recently tell me that they chose to do this on Linux by default, and observed a considerable performance benefit in their executable and reduced, well, obviously reduced binary size. If it didn't export everything by default, it doesn't have to generate all of the functions into the DLL or into the SO. Just an aside, I have not played with it myself, but I was like, that is interesting, and I will have to try it myself at some point.
I've read about that. I haven't done any back and forth testing, and I'm not much of an expert on shared libraries. I know how to work with them, but I can't tell you exactly why what Jason said is true. But yeah, that's true. There are other benefits to hiding all symbols by default. Even if you don't support Windows, that might still be something you want to do. And thus, if you want to hide all symbols by default, then you're opting into this extra stuff. So even if you're not supporting DLLs, this is probably something that you still should learn about. So goes a little bit deeper. So this generate export header is generating a header, it's generating code. So by default, it'll generate it into your binary directory. I strongly recommend you stick by that. Don't take generated code and put it in source control. The file it generates changes by platform. So if you try to put this in source control, someone on a different platform will generate different code, and that will be ugly. So let it, by default, keep generating into the binary directory. What that implies is that now you have an extra header that you have to find, which is what this line right here is doing. This line is saying, look in your binary directory /include. I just mirrored the structure between the source and the binary directory. Look in this directory for this particular header. It has that same argon prefix that all the rest of the headers have for the sake of consistency. So when you're actually writing the code or reading the code, you don't really know that it's generated code. It's all kind of conveniently invisible to you. And if you go back to the installation slide, you'll notice that there's an extra argument to install the contents of this directory. So that's one more thing they have to remember. Lastly, when you're actually building a static library, so notice if it's not shared, so if you're doing a static library build, you have to define this macro. Argon static define is something that is in that export header. You can tweak all the settings if you want that to be something different than your target name _ static define. You can configure all this stuff. There's 10 or so arguments to generate an export header if you really want to tweak all these things. But this is another one of those things that you just have to deal with. If you're building static libraries, you now have to add this additional define, but when you put it in the build system, it just all automatically works, so it's not too much of a problem. And then lastly, this is a bit of the C++ code. When you're actually using these things, you'll have a macro called the name of your target _ export. Again, that's a configurable name if you want something different. So before every symbol that you want to export, you have to include that definition and explicitly opt in to exporting that in your shared library. So all of this stuff shows that shared libraries, when you're doing them in a totally cross-platform generic way, add a lot of overhead. But ultimately, I think it's a good thing, and you should consider supporting it. All right, that's most of the heavy stuff out of the way. This is more kind of sugary things that you maybe haven't thought of, but I think they should hopefully be a little easier to wrap your head around. So a popular way to consume or build CMake projects is to compose them. So that means that someone will actually take your library and they will configure all of that within their project. So in a sense, it's almost as if they're taking that third-party code and saying, now it's first-party code. They're building their project directly alongside yours. And that's very convenient. You'll see this is what's happening when people use fetch content or external project, or they'll use like a git submodule and then call add subdirectory to include your library. But when you do that, you need to be careful because you don't want them to be building your examples or your test or your docs. There's a number of things that only matter when you're building the library by itself, and you want to hide those. So again, with Hiram's law, if you're not familiar with that, basically says that anything that you can observe will be observed. So in this case, if users can observe the fact that they can build your test, they're going to start depending on that. So if one day you take away the ability for them to build your test, then you're going to have angry users. So it's best to cut these things off early on in the lifetime of your project. So the way that I do this is that near the bottom of my top level CMake script, I have this conditional right here, and it's saying if project is not top level. That basically means if this project is currently being consumed. And what I do there is I just return. So everything below this is only ever configured if you're building the project as the top level project. So if you're developing the library, that's the case. Even if you're packaging the library, you're building the library by itself. It will configure all of these, but for anyone using add subdirectory through whatever means, they automatically short circuit all of this early return. So what's great about this is that anything here is safe. You can change as much as you want, whenever you want. There's no way for users to depend on this in a way that is actually reasonable. Of course, I'm sure hacks exist, but anyways, it's great because you have the ability to change this whenever you want.
Is that variable built into CMake?
Yes, good question. That is a feature from, I want to say 3.20 or 3.21. So it's relatively modern, I think sometime in the last year. I suppose I'll reiterate, I'm assuming that you have 3.22, which is the version of CMake that ships in the latest version of Ubuntu LTS. I think that's a good balance of new enough that you get a lot of really convenient features, but it's still old enough that it's safe to assume that a lot, if not all of your users of your library will have access to this. A 21 feature, okay. So yeah, it's pretty new. These new features you maybe haven't seen a lot because libraries are typically very conservative about what CMake version they use. I'd argue probably too conservative, but yeah, if you're unsure what to use, 3.22 is a good version to go with.
I did want to point out that you can install CMake, so you can always get the link from the CMake wiki.
There's a great article that goes over that I can share with anyone after this by someone called Alex Reinking that I'd recommend, called CMake Without the Agonizing Pain. There's 2 of them out. Insider info, article 3 is coming out soon. So you should definitely read that again. Alex Reinking, he's got 2 articles that are really great. And if you're hanging around afterward, I can send you the links for those. But yeah, he goes over all the various ways you can install CMake. So that's a whole other thing. I would say compiler warnings and minimum versions are like the 2 most controversial things. And I'll talk for like hours about it if someone wants to. But it's a whole thing. Which version you pick. So another thing, this is something that I only learned pretty recently, and it's like a pretty trick thing you can do. I haven't seen a project use this before, but I think it's pretty neat. So before you actually define your library, what you can do is you can again say if it's not top level, which is basically saying if it's being consumed. We have this variable called warning guard, which just expands to the keyword system. And then it's used in the target include directories call. So if you're not aware, public means it's used by the project and by its consumers. System public means, again, it's used by the project and its consumers, but it's treated as a system header. So on something like Clang or GCC, that expands to the -i system flag. And basically what that means is that you won't get warnings emitted for it. You don't want warnings to appear in your third-party code because you don't own it, you can't modify it. It's very annoying when they appear. They're noisy in the console. Sometimes they can break the build if you don't configure things correctly. So what this is doing is saying that when people consume your project, it automatically adds system. So this is a really nice convenience for your users, and it means that you as a library author, you're not going to get bug reports complaining that people consumed your library via like fetch content or something, and then like now there's warnings because they use some obscure warning that you don't build with, and then it's breaking their build because of your code, and you don't want to fix the warning because it's an opinionated warning. You can skip all of that by just doing this little trick right here. Done.
If you're not able to use 321, was it? You can simulate project as top level by comparing CMake source dir to CMake current source dir. There are a couple of things you can do like that.
Yeah, that's a good point. I think there's a few ways that you can simulate what project is top level is doing. Ben said you can compare the source directory to the current source directory. That should work. I've also done comparing the project name to the current project name, although that's weird because you can give your project the same name as the library you're consuming. So that's a little weird. So yeah, there are ways to approximate this using much older versions of CMake.
Another comment here. I think this only will suppress the warnings in headers. I think if you have warnings in your implementations, it still would potentially flag.
But theoretically, what else is assuming that they're not going to see your implementation?
Oh.
If they consume it via add directory, they're compiling it all. So if you're not careful, you can globally enable compiler warnings before it applies those warnings to a third-party project. So you can fix this by like consuming the third-party project, then applying your warnings. That relies on the user knowing how to do that and actually doing it. I understand all of these things are kind of hacks around just using a package manager. Use a package manager if you can. A lot of people can't or won't. But if you use a package manager, a lot of this stuff doesn't really apply.
So what I do is I put my warnings in an interface-only warnings library, which I link, and then they're not global. They don't leak out.
Like I said, warnings are controversial. I would take up all of my friend Tyler's time if I went into that. So we can talk about that later. I personally don't prefer applying warnings from targets, but that is an option. If you apply warnings on a per target basis, then you won't accidentally apply warnings to an external project. I'll also note that right here, this is an alias. So Argon : Argon is an alias to the Argon library. In a previous slide, I mentioned that in the install interface, I apply that Argon : namespace to the targets. What this does is that if someone consumes this library through, like, say, a package manager, they'll only get the argon argon target. But if they consume it via add subdirectory, that target should still be there. So you just need to add an alias to point to that. And later I'll show you how you can write tests that check that all this stuff exists. So for Doxygen, I've seen a couple ways of using Doxygen. This is the solution that I've settled on, is that I have a doc/CMake lists.txt file. It attempts to find Doxygen. If it doesn't find it, fine, no problem, just return from this file, it's not a big deal. But if you do have Doxygen installed, which if you're the developer, you probably do, then what it's doing is it'll download a CSS style sheet from the web. It sets a few options for how I specifically want my Doxygen site to be built. There's a lot of these. What's great about this is that you can use all the CMake variables that you know about to get very particular about how you configure it. And at the end, there is this function right here, which I believe comes from find package Doxygen, which is doing the final generation. So I've seen projects that have like 1,000-line doxy file in them. That still works if you prefer that, but it's not a requirement. If you want to just generate that yourself, you can. All you need is this much code, and you get your Doxygen website. I also have a GitHub action that deploys this. I didn't want to get into pipelines in this talk because I only am trying to give myself about 30 minutes, but I do also deploy this to the web. And if you go to the, yeah, right there, there's the actual docs website. So if you want to open that up, you can see what all this generates into. I use Clang format and Clang tidy on all my projects, and the specific way that I like to use them is via CMake targets. So I use add custom target to have a target called format for Clang format and tidy for Clang tidy. For Clang format, I shell out, I use get ls files to collect all the headers and source files, and I pass that to Clang format. And then I can also tell CMake to run that from the source dir. So if you build this target from anywhere, no matter where your binary directory is, it'll always run Clang format from the right directory. And then for Clang tidy, you kind of need to use this with your build system because Clang tidy expects a compile commands database, and that is generated by CMake. It lives within your binary directory. The only robust way to know where to point Clang tidy is to invoke it through your build system. So what this means is that the tidy target, no matter where you run it, will always know where to find that compile commands database. I use run Clang tidy, which is a script, a Python script from the LLVM project. For the most part, it just runs Clang tidy in parallel. So it's significantly faster than running Clang tidy by itself. And an important thing to note is that run Clang tidy will parse the compile commands database for all your .cpp files, and it will automatically analyze all of those. If you just run Clang tidy by itself, you then have to do something similar to this, where you need some expression that lists all of your source files, but run Clang tidy solves a lot of that for you. Jason?
Are you opposed to the built-in tidy format?
My problem, so there is a built-in Clang tidy integration within CMake, but my issue with it is that you need to, it'll run Clang tidy while you build. And for some people that might be exactly what you want, where Clang tidy is always running. But the problem is if you don't want to run Clang tidy, you now have to reconfigure your project to disable some option. So if you want to run Clang tidy, let's say you build your code, it's working, you're like, oh right, I want to run Clang tidy. You now have to go into your cache, change the value of the variable, and then reconfigure the whole project and then rebuild it and then run Clang tidy. I personally would rather just run like make tidy or ninja tidy. I just build the tidy target. That lets me do stuff like I can run Ninja is the build system I typically use. I will run Ninja all format tidy. So all means it'll build the whole project, including the test examples, all that. Format will reformat it, tidy will run Clang tidy. And then if all of that passes, then great, I'm in a good state. It's probably good to go ahead and commit. And that workflow has worked really well for me. So for testing the install interface, this is something that I think is really valuable for libraries, because if you don't test your install interface, there's a lot of ways that you can break it and not really know until some user complains. So this is actually my example program. So in the examples directory, this is the one, this is the build script, and there's just like a single source file. So for the most part, it's kind of what you'd expect from a minimal example using the library. You specify your version, project name, you find a library, you make your target, you link it to the library. The key difference here is that, again, project is top level. It's like my favorite feature. You're saying if you're building this project by itself, so if you directly configure this, then it will go call find package. So what I do in my CI script is that I first install the library, and then I configure this project and I point it at the install that I just installed. And then it finds that and it configures with it. And then when I build the library normally, it also builds this, except this part gets skipped. So when it gets to here, it's linking against the version of Argon that is part of the same project. So if you forgot that alias library from before, this line would fail because of you missing that target. And then if in your install interface, you change the name of the install target, then your install test would break, but your build would still succeed. Likewise, if you forget to install like that export header, that generated export header, if you forget to install that, that'll come up. If you forget to install certain headers, a number of things. If you forget to export symbols, that'll get caught, although your test will also catch that. In either case, I think this is a really nice pattern for not only showing how to use your library, but also using this to test your install interface. So if you're making shared objects in the Unix world, there's an assumption that you're going to have extra symlinks. So I believe the actual file on disk is that bottom one, libarcon so 012.0. But there's one or two symlinks to that is typically expected. So when you set the property called version, that is the version of the shared object, that is how you get that 0.12.0 suffix on it, because I have it configured to use just the project version. It can be whatever you want though. There's another property called SO version, just all caps SO version, which will give you the libargon.so a single number. So if you want to specify like ABI compatibility, you can have your SO version be something like just the major version of the library, for example. If your policy is that all major versions have the same ABI, you can do that. Maybe you have the same major.minor. So within a given minor release series, you have the same SO version. So this is another one of those things that is probably going to be expected of your shared library. Presets are a feature that's from CMake 3.19, so it's about a year old at this point. This is another feature that I think is really great, but it's not seeing a ton of adoption yet because a lot of projects are still requiring even older versions of CMake. So this is a JSON file that defines basically all the flags that you'd be passing to CMake when you configure, build, test the library. So in this case, you're looking at the configure presets, and I have one called dev, and this is just like my generic, I'm developing the library preset. So I have a binary directory, which is called build. It's build within the source dir. I set the installer to build install, so that if I try to install the project, it installs within the binary directory instead of trying to install to the system, because when I'm developing, I don't want to install to my system. It'll complain about not having super user access, and I don't want to deal with that. So I specify the installer, and then a few other variables that I like to use. So I do a debug build, I turn off extensions, and I enable the compile commands database that clean tidy needs. Using it is that first command, CMake -s preset dev. That's it. What's great about this is that if you're working on a team, you can say our workflow is to use some given preset, and then you can just modify the preset in source control, commit it, push it, and then when people pull that in, they'll just automatically start using that new preset. So you don't need to tell developers to add an additional flag when they build your project. For projects that have like complicated ways of running tests or just generally require a lot of flags to work in the right way, this is a really great feature. After you use the preset, then you're just building it like normal. So there are build presets. If you have like a complicated build command, you can have a preset that encapsulates all those build commands. In my case, library is simple enough that I'm just doing a generic build, so I only use configure presets. And I think for the most part, configure presets are the majority of the value in presets. They do get more sophisticated, but you can generally ignore the other types of presets for at least while you're learning. So I have a preset for code coverage. Some projects like to enable this within the build. I think you don't need to do that. So for simple projects, you can just have a preset that adds the -- coverage flag. Then in CI, I have all like the gcov commands to actually process that. But there's no reason you need to have like a project name enable coverage flag, and then like an additional conditional, and then some extra code to apply the flag. You can just do it in a preset, keep it out of your library. A theme you'll notice with presets is that it's usually about taking code that doesn't really need to be in your build scripts, and it moves it out. And there's a lot of benefits to that.
So how did the variables, like if you define a variable in one preset and then you build that, and then you have another preset that doesn't define that variable, does that variable stick around? Like how do they, are you able to cleanly switch between profiles for presets?
It's kind of hard to say. So presets have this concept of inheriting. So like here I'm seeing the coverage preset inherits from dev. So this preset includes everything from this one. I lost track of the rest of your question though.
Like if you didn't have that, and you ran this preset and then you ran the coverage preset, would the build type still be set to debug, or would it get reset to whatever some
It would
default is?
change. There's things related to how CMake caches work that if you don't override a value in the cache, it will keep using what was cached. So if you want to switch presets and be absolutely sure that the entire state of the last build is gone, you need to either delete the cache or just delete your whole build directory, or there's a -- fresh flag that's rather new that you can use as well. But like hot swapping between presets, it will probably do what you want. I mean, certainly anything that you specify in your preset will override what is already in the cache, but existing cache variables will stick around.
I forget, one of the minor versions of the 20, you can specify.
So it's probably a good idea to think of presets like you think of tool chains. So switching them involves more or less blowing everything away. You can specify tool chains in the presets. So that's how I think of them.
Yeah, you can specify tool chains in the preset as well. So package managers like Conan will take advantage of this. They'll generate a file called CMake user presets, and they'll have the tool chain specified, since Conan typically works with tool chain files. Typically, but not always. It'll automatically apply that. So there's a lot you can do. There's a lot more than what I'm showing here, so I would definitely recommend looking at the docs. Every single minor release of CMake is adding a lot to presets, so the feature is obviously getting a lot of attention. The developers, kitware, really care about it, so I think it's a good feature to invest in. That was code coverage. And then I also use it for sanitizers. So I have a preset for Clang tools, which just double checks that you're using Clang as your C++ compiler. That inherits from the dev preset that you saw before. And then on top of that, I have an ASAN and a UBSAN preset that inherit from Clang tools, which add the specific flags related to applying sanitizers. So this, once you get to here, we're getting into pretty messy territory with how many flags that we're applying to the compiler. So it's nice to not clutter up your build scripts with this. You don't want an incorrect application of a sanitizer flag breaking the build of someone who's just trying to use your library. That's a liability if you want to put it in your build scripts. But when you put it in your presets, I should note the expectation is that users will not use your preset, not necessarily. People packaging your library won't be using it. It really only exists for you. So you can kind of go wild with whatever you want to put in there. So it works great for sanitizers like this. Should you add all these things? Maybe. In the case of this little command line argument parsing library, this is way over-engineered. This library exists for me to test out these things, which is why I use these all. If you have a library that is of this scale, which is to say maybe 100, 150 lines of C++, probably don't bother. Unless you enjoy it like me, don't struggle, don't hit your head against the wall trying to get this stuff to work. But certainly if you have a library that is of scale, that is into the thousands, tens, maybe 100,000 lines of code, these things do become much, much more useful. As your user base grows, the things I showed about hiding warnings and hiding things like your tests from downstream projects, those become a lot more important. So use your discretion. If you think a feature, something that I showed is going to be useful, please do it. But if you look at the slide and you're like, I don't care, like the DLLs, I don't care, don't stress about it. That's all. Thank you very much.